Okay, last time we just started multiple quantifiers and negating sentences. So we're still in this unit 2 logic. We talk about the quantifiers. There are two types of quantifiers. One is called the universal quantifier. It's like inverted A, capital A. And then, up and down. Uh, the other one is called existential quantifier. That's like a capital E flip left and right. Flip to the or reflection to the left. We use that a lot, especially in the proofs, in mathematical proofs. One of the things is when we have a statements with multiple quantifiers, when you have multiple variables in open sentence, for example, then you will need multiple quantifiers to specify the values for all the variables. And then there is a problem, a question of the order of the quantifiers. And it turns out the order is important. And we have already seen one example last time. So, when you have a statement with multiple quantifiers, if you change the order of the quantifiers, then the truth value of the statement will change. So, for example, I don't know whether this was the example we did last time or not. I think that's probably no. We talk about a different example. We used both quantifiers in the previous example, and switch the order of the quantifiers, and we see they're not the same. Okay, but when we use the same quantifiers in the statement, then the order is actually not important. For example, if we have the statement of for any x in R and any y in R, x greater than y. So that's a statement, and we know that's false. If we choose arbitrary values of x and y, you cannot say x is always greater than y. So that's a false statement. If you switch the order of the two quantifiers, x and y, basically, then you say for arbitrary y in R and for arbitrary x in R, x is greater than y. That's the same thing as the previous one because you just choose x and y arbitrarily. The order is not really important, because they're arbitrarily chosen. That's still false. For arbitrary real numbers, y arbitrary real number x is always greater than y. That's false, of course. So in that case, we can actually use a shorthand for this notation of the two quantifiers, which are actually the same quantifier. We can write in a short notation as arbitrary x and y in R, x greater than y, or for all x and y in R, we have x greater than y. So that's the same thing as the other two. and it's still a false statement, of course. And similarly for the other quantifier, the existential quantifier, they're always not important if there are both quantifiers are the existential quantifiers. We just talked about the universal quantifiers. Now we talk about existential quantifier. If there are both existential quantifier, then the order is not important. For example, suppose we have statement there exists x in R and there exists y in R such that x greater than y. Of course, that's true, You can always find the two numbers and one is greater than the other, right? Or if you switch the order of this x and y with the existential quantifier, then you would say there exists some y in R and there exists some x in R for which x is greater than y. And again, this order doesn't matter. Of course, you can find, any pairs of those numbers. Either you pick up y or x first, doesn't matter, You can always find two numbers, one is greater than the other. So this is also true. So they give the same truth value. So they're equivalent. So order is not important. So in that case, as the previous one shows, you can use a short notation in this case to write that there exists x, y in R such that x is greater than y, or there are real numbers x and y such that x is greater than y. All right. So the order is important only when you use different universal or existential quantifiers in the same statement. Well, one of the things when we use the quantifiers, if the domain of a variable is well understood, then you can actually write it more concisely. You can change the notation a little bit. For example, if x, y are variables with domain R, and you wish to express the statement, every positive number has a positive real square root, and we know that's a true statement, by the way. The original notation will be when x belong to R greater than 0, there exists some y also in R greater than 0, so that x equals y squared. So every positive real number x, so that's universal arbitrary x, has a positive real square. So there exists some y also positive, such that the x equals y squared. So there's such that y is the square root of x, a positive root. So the set notation R with footnote greater than 0 or subscript greater than 0, that's the short notation for positive real numbers. But since, if you don't specify this x and y are real numbers, then it is understood that we're talking about real numbers. If we don't say it specifically, then we know we are talking about real numbers. That's for by fault. So then we can write this statement in a short notation in symbolic logic as for object x greater than 0, exists y greater than 0 such that x equal to y squared. Okay, so we don't need to write this y greater than 0 set notation and belonging to just write arbitrary x greater than 0 because there exists y greater than 0. That's good enough, and we have seen that a lot before. Okay. So another example of this kind of modification notation is in the definition of the limit of function. This is the notation for the limit of function. So the limit of function f as x approaches a is equal to L. That actually defined as this. If you use sigma, epsilon data notation, this is a short notation for this whole thing. Okay. Although we did not talk about this notation quite a bit. I don't know if you actually learned this notation or not before in calculus. Most people didn't, introduce this notation or definition of limit. That's the rigorous mathematical definition for the limit of function. We didn't use x in R or L in all those because this is obvious. Okay, we're talking about real numbers. If we don't specify. Okay. So by the way, the definition of this limit is for any arbitrary epsilon greater than 0, so any positive number, there exists another positive number that may depend on the first positive number. So we call the second positive number delta, so that for any real number x, if the absolute value of x minus a is greater than 0 and less than delta, and then we can conclude or implies that the absolute value of fx minus some number L is less than epsilon. Okay, so that's the formal definition of limit. You really don't need to write this arbitrary x in R, as we know that we're talking about real numbers. So you just write the other part. For this definition of limit, it essentially means you can get as close as you want for the function value, as close as you want to L. So less than epsilon for arbitrary epsilon greater than 0. So this epsilon can be arbitrarily small. So that this conclusion here, this statement Q essentially means that you can get as close as you want to L. In the condition that x is sufficiently close to delta, so the absolute of x minus a is less than delta. So if you're given a small number epsilon, for example, then you can always find another small number delta, so that when x is within that the range of data close to A, then you can guarantee that the function value f is as close as you want to L. So that's the precise definition of a limit of a function, meaning you can the function value is close to L as the extent as you want. If you let x approach a sufficiently sufficiently closely. All right, but let's just not spend time on more time on this, not focus of this course. But just to give you some, short notations. Sometimes when the domain of the variables are understood, you don't need to write it down specifically. Okay, so that's the first part from multiple quantifiers. The next thing in this section is negating sanities. So this happens when we have a compound statement or open sentence. How do you negate it? So usually negating a statement can be done by placing words. It's not the case that in front of the statement or open sentence. Or the negation of statement P can be interpreted as P is false. Okay, right? So negation of it. But it will be a little more complicated when you try to negate a compounded sentence. This is especially true when we have some conditional statements or open sentences. Okay, even that we can use the rules, the logics, the rules for we talked about it before to simplify the situation. For example, okay, if we wish to negate a statement P and Q, we could write the result as the negate of parentheses P and Q. But if we use De Morgan's law, that's actually equivalent to negation of P disjoint. I mean, yes, disjoint with negation of Q, right? So we can say that negation with statement P and Q is also equivalent to the statement negation P or disjoint negation Q. And sometimes this saves a lot of work. Okay, so this is a typical example that why you want to use the those rules to simplify logic statements. If we wish to negate the statement P implies Q, where P and Q are statements, okay, you want to negate this in this example. So if you look at the examples or the rules or exercises, you might recall this conditional statement P implies Q is equivalent to negation of P disjoint with Q. And this is easy to show, by the way, to prove by join a truth value table, right? That's a very direct way to prove it. Okay, just make a table with P and Q in the columns. So then you can choose P either true or false, and the Q either choose true or false, and then the combination of P and Q we will have 4 possibilities, and then you just find out negation of Q and P, and then you do the disjoint with Q on the other columns, and you can see these 2 compound statement give the same truth value. Exactly. So they're equivalent. So then now we can use that equivalence to do the negation of the conditional statement, P implies Q. So if you try to negate P implies Q, then because P implies Q is equivalent to negation P disjoint with Q, then you just negate that thing. Okay, and then you can use the De Morgan's law to change this disjoint as intersection or conjunction, and at the same time you negate each compound statement. So you're going to negate negation of P and negate Q. But the negation of negation P is just P itself. So at the end, that's just equivalent to P conjunction to negation of Q. So this simplifies the situation, because when you have a conditional statement, it's very hard to think how to negate it. But to work with conjunction will be pretty straight, isn't it? And if you try to translate those 2 statements in words, you can say P implies Q is false. Okay, so that's the left-hand side of negation of P implies Q, this conditional statement. So it says P implies Q is false, though. So P does not imply Q, okay, basically. And it's the same as P is true and Q is false. Okay, so when on the right-hand side, when P is true and Q is false, then you get the negation of Q true. So the whole statement on the right side is true. Okay, so when the left-hand side is true, or the negation of the conditional statement from P to Q means P implies Q is false. Okay, so that's when the left-hand side is true, okay, because negating this P implying Q. So you should say P implying Q is false. So that's when the left hand is true. What happens if the right hand side is true? It has to be P true and Q false. So in other words, P implies Q is false is the same as P is true and Q is false, right? Because the conditional statement is false only when P is true and Q is false. So if you say P implies Q is false, that means P is true and the Q is false. Okay, so exactly what it means by this conditional statement, isn't it? All right. Any questions? Nope. Okay. So the next thing is important. It's very important. So this tells, how to deal with negation of statements or open sentences with quantifiers. Okay. So suppose Px is open sentence where X has domain S. All right. So suppose we have statement for operator X in S, Px. So that's a statement because we specified X in S. Okay. So if you try to negate this statement, you would change the universal quantifier into existential quantifier. So these are two quantifiers. When you negate, they just change to the other. Okay. At the same time, you also change the or negate this the open sentence P. Okay. So when you negate the first statement, you say for any X in S, or all of the X in S, Px. Okay. So Px is true. If you want to negate it, that means that's not true. The whole thing is not true. So there must be some value of X in S for which Px is not true. So that's exactly what it means in here. There exists some X in S so that the negation of P is true or P is false, right? Similarly, when you have a statement with quantify the existential quantifier, and you want to negate it, you just change that into universal quantifier, and at the same time you negate the open statement. So, for example, if you say there exists some value of X in S so that P of X is true, that's a statement. So if you want to negate it, so that means there's no X in S so that P is true. So that means for all of X in S, P must be false, right? P must be false. So that's exactly what in here. So you change the existential quantifier to universal quantifier to say for arbitrary X in S, or for all of X in S, the negation of P of X is true or Px is false itself. So you negate the P at the same time, right? So that's how you negate statements with quantifiers. So the rule is you need to change the universal quantifier to existential quantifier or vice versa. And at the same time, you also negate the open sentence. All right, keep in mind. So let's just do some examples. Suppose I wish to negate a statement that all integers are positive. So we know that's not true. So first, let's just try to write this in symbolic logic. Okay, so we can use the universal quantifier all integers. So that means we need to use universal quantifier for any X in Z integers. So okay, X is greater than that. So that's exactly what it means. All integers are positive. So we use P to denote this statement. According to the rule on the previous page, this actually said as axiom. Okay, so you don't have to prove it. So this is given. This has to be true. So this is given. You just use it. Okay, so if we want to negate this statement, then we're going to change the universal quantifier into existential quantifier. At the same time, you negate the open sentence. Okay, so the negation of P will be there exists some X in Z or some integer X. so that the negation of x greater than is true. If you think about the negation of x greater than 0 or positive, then the negation of that is just 0 or negative numbers, right? So x either 0 or negative. So there exists some integers x so that x is either 0 or negative. Well, of course, that's true. Okay, so when you negate the first statement, which is false, then you're going to get a good true statement, of course. So you say there exists an integer that is not positive, okay? Or some integer is not positive. Or some integer is 0 or negative, all right? So you can write the negation of P as there exists x in Z is such that x less than 0, less than or equal to 0, as we just discussed. And we know that's true. Okay. And the next thing is a little bit more complicated when you have more than two, one quantifiers used at the same time. How do you negate the sentence, the statement when you have a statement with multiple variables and multiple quantifiers? How do you negate that statement? All right. So the x, y, z be variables with domain s, t, and u, respectively. Okay, so these are some variables with different domains, and let P of x, y, z be an open sentence. And so, so you can use universal quantifiers and the existential quantifier at the same time to these variables to make a statement. For example, we can make a statement as for arbitrary for any x in S and for any y in T, there exists some z in U such that P of x, y, z is true. Okay. So how do you negate this thing? Negate this statement. So we have several levels or layers of this statement that we can actually break it down into several steps when you try to negate it. And one way to do it is just to use parentheses to separate each layer. Okay. So in order to do this, to negate the statement, we will use parentheses to make the order of the quantifiers clear. Okay, right? Hence, the statement that we wish to negate is, okay, so first just use parentheses to separate those quantifiers, layer by layer. And then you just do the negation one level at a time. Okay, so for example, so we want to negate this whole thing, so we add another parenthesis to the whole thing. And then what happens is, so you negate this, all right? So the first thing to do is to change the universal quantifier when x in S, you change that to there exists x in S. Okay, as we know that we talk about this, and then you negate the other part following it. Okay, you make the parentheses to make the other things as one part. Okay, then you negate the remaining part. And for that again, because this has two layers, so you can change the universal quantifier for y to existential quantifier for y. So there exists y in T, and then you negate the remaining part. Okay, that's in the parentheses. That's one part. Okay, and do the same thing. The remainder is easy. It only has one quantifier, so they can you just negate it directly by changing the existential quantifier on Z to the universal quantifier. So you write the exist. I mean, for arbitrary Z in U, and then you negate the P, so that P is not true. Okay, so at the end, the negation of this whole statement is there exists some X in S and some Y in T, so that for any Z in U, the the statement P of XYZ is false. Okay. Uh, so so one thing important, you notice that negating this quantified statement was as simple as swapping all existential universal quantifiers and negating the open sentence at the end. Okay, so that's the rule we summarize from this problem. When you have multiple quantifiers, multiple variables in a statement, you just swap the existential quantifier and the universal quantifier each time. And then you negate the open sentence at the end. All right. Okay, one of the things that needs to be especially careful is when you try to negate a statement with quantifiers. It's easy to make a mistake, especially when you change the universal quantifier to existential quantifier and vice versa. You do not change the benign to not benign at the same time. You only change the swap the quantifiers. You do not change other things in that part. Of course, you need to negate the open sentence, but for the universal, for the quantifiers part, you don't change everything else. You just swap the quantifiers. That's one thing that has to be cautious. One of the things when you change this benign to S to not benign to S, then you change the domain of the variable, basically. All right, and the whole statement may not have a truth value, or even doesn't make sense because you are talking about it and the variable not in the domain, right? Okay, let's say let's look at one more problem. Okay, so this kind of problem you change change the benign to or other parts of the quantifier. It happens usually when you have some other other notations, other relations. Okay. So the problem mentioned in the previous warning most commonly happens when we use notation other than x belonging to s, quantifiers. Okay, so in this case, it's greater than instead of belonging to. So in this time, so for instance, for x is a real variable and we wish to negate this statement of arbitrary x greater than 0, px is true. The correct answer is, I want to negate this statement. There exists x greater than 0 such that the negation of p is true or p is false. Okay. So you don't change this x greater than 0 to x less than equal to 0. because it's x greater than 0. It's shorthand for x belong to r greater than 0, right? So you don't change that to benign to not benign to. Okay. So you just keep it x greater than 0. Okay. Let's do one more example. Suppose we want to negate the statement of P, which is for any x in R, the exists y in R such that x is greater than y. We know that's true. For any real numbers, you can always find another real number so that the first number is greater than the second, right? If you try to negate it, then you swap the quantifiers. So then you are gonna get there exists some x in R and for any y in R. Okay, swap the quantifiers, and you need to negate the open sentence from x greater than y to x less than equal to. So the whole thing becomes there is some real number x for any real number y. You have x less than equal to y, and that's a false, right? Because for any number y, you cannot find for all real numbers, you cannot find the number x to be less than equal to. Okay, you cannot find the smallest number in the real numbers, basically. All right, and we talked about that before, actually. That's false statement, and that should be the case because the first statement P is true. So negation of P should be false. Okay, I guess we're gonna stop here today and finish this section next time, next Monday. Any questions about this quantifiers and negations?